Today I'm here to present our research paper on enhanced segmentation and deep learning architecture for early diabetic retinopathy. So I'm Renato R. Maaliw III. So on behalf of my co-authors, it is my honor to present this research. So for the introduction, so diabetic or the excessive sugar levels retinopathy is a serious complication needing prompt diagnosis and medication to avert vision loss. So lesions caused by the condition are difficult to track because they are hidden behind the eye's structure. Most of the time, ophthalmologists manually evaluate scans to spot the abnormalities. Today, experts in computer vision are starting to pay significant attention to automatic diabetic retinopathy detection. Since the image segmentation's output is critical to classification success, it has been the subject of numerous papers based on literature. Existing literature cites that there are different methods and advantages and also disadvantages in diabetic retinopathy detection. But we are confident that there are still gaps in terms of its early detection. In the advanced stage of diabetic retinopathy, vascular markings are noticeable. However, it is not the case for early and mild conditions. As a contribution to science, we propose a pipeline with extensive pre-processing techniques, enhanced segmentation algorithms with atrus pyramid pooling, and a modularized attention-aware deep CNN for diabetic retinopathy classification. So our study can assist eye expert in reliably predicting its progression at the earliest possible time for necessary treatment using artificial intelligence. So for the methodology, so we gathered 388 high-resolution fundus images divided equally to two independent groups with the normal and the presence of diabetic retinopathy. It's diaret DB1, diaret DB, and 0. So the link to the datasets can be found on the full paper. So images are normalized because it has different sizes to 5 by 12 by 5 by 12 pixels to compensate for size differences and for uniformity. So here are some sample images that exhibits diabetic retinopathy, including a normal eye, as you can see on the letter J. So for the data augmentation, so we applied a geometric transformation in order to increase the data set as neural networks rely mostly on a big data set. So with a total of additional 1,552, a total of 190, 40 images based from flipping and rotations of images. So we have 970 for each class. So an 80-20 training testing split with turn early cases of DR samples excluded using a tenfold cross validation. So for the color adjustment, so we noticed that the green channel produces more details than the red and the blue ones. So as a pre-processing technique, so we converted the images using a grayscale bot under the green channel. So we developed an enhanced segmentation technique. So we modified the unit architecture, a standard unit architecture to address lesion, exudate, and microaneurysm using semantic segmentation. There are three major parts on our segmentation technique: the encoder, the bottleneck, and the decoder. So this is the detailed implementation of the segmentation algorithm. So I want to discuss this one, but the full explanation and implementation of this is can be found on the paper. So we also design a modified attention-aware deep CNN, so including three subsection for segmentation adjustment, for lesion consciousness, and the DR detection subnetworks based on residual nets, and we also use the mark mask RCNN. So this is the model that we propose for the architecture. So we pre-train on ImageNet, then we have segmentation contraction, then we have the lesion detection, with concatenation. Then we have also the DR classification subnetwork. So we will classify the images into normal and the presence of diabetic retinopathy. So more on this on the explanation of this side in the full paper. So for the evaluation metrics, we use IOU and dissimilarity coefficient. So for classification, accuracy, precision, sensitivity, and specificity. So these are the equations for our evaluation metrics. So for the result, so we optimize the hyperparameter of our deep convolutional neural network by a base search optimization. So if you want to replicate this research, these are the hyperparameter set on each the specific convolutional neural network. So for segmentation performance, so we called our segmentation the DR unit or the diabetic retinopathy unit. So it performs very well, as you can see, with 8871 and 845, surpassing the standard unit and the standard residual unit architecture. For segmentation performance, here are the example. For the input images, the ground truth mask, and the segmentation of our DR unit. For the classification, so we benchmark based on literature. It shows that our proposed DR unit with attribute spatial pyramid pooling plus attention-aware deep convolutional neural networks is outperforms other existing models with accuracy of 99.20%. In terms of confusion matrix, so in terms of the DR, so only one misclassification. And in terms of normal to DR, only two misclassifications. So for the classification performance, so we use 10 early cases of diabetic retinopathy. So our model predicted 9 out of 10 with the misclassification on letter J, as you can see. The ground truth is diabetic retinopathy, but our model predicted is normal. So 9 out of 10 in terms of early DR images. So for our model and training validation loss, so as you can see in the graph, we have a gradual convergence. So it converges at the 85 epoch. It so as you can see also on the line, it actually shows no signs of under or overfitting. So this study introduced an enhanced segmentation technique we call DR unit and attention-aware DCNN for diabetic retinopathy detection. So based on our benchmark, our DL unit performs very well than other standard unit and residual unit based on the benchmark values. So compared with the different existing techniques, our proposed attention aware with multiple subnetworks architecture attain 99.20% classification accuracy. Furthermore, the model's exceptional performance was validated by its capability to detect even early signs of diabetic retinopathy using a validation set. So our training and validation loss exhibited slow given the complexity of the model, but gradual and smooth convergence rate, showing no signs of over and underfitting. So as per limitation, we did not examine methods for improving image quality on the pre-processing side, such as image dehazing and spatial filtering, because we encountered a noisy and low quality fundus images that can lead to segmentation and classification. Let's move on the conclusion in future works. So DR is a severe consequence of diabetes that can cause significant vision loss or even blindness if not detected and treated properly. We developed two strategies to boost lesion detection in diabetic retinopathy. So we use an enhanced segmentation framework and a modified CNN architecture using Atrius spatial pyramid pooling that discards irrelevant regions from fundus images. Nevertheless, we observe it is prone to oversegmentation. That is why we designed a DCNN to adjust the segmentation fittings. So stacks of residual nets with pre-trained base and different features proved to be robust in DR identification, including early stages. So our research will significantly contribute to the medical image prognosis to identify DR automatically and non-invasively. So AI can really supplement human expertise. It is really most effective when paired with traditional healthcare practices to provide patients with the possible comprehensive care possible. So by consolidating the strength of both approaches, we can create a healthcare system that is more efficient and effective at meeting the patient needs. So for future work, we intend to create a better neural network design in the future to classify based on DR levels or severities. Thank you very much for listening.